A very good evening to the invited speaker of the day and all the participants. It's my pleasure to extend a cheerful welcome to you all to the introductory session on microwave engineering, which is organized by IEEE Microwave Theory and Technique Society, Student Branch Chapter, University of Peradeniya. This event was organized with the aim of providing you the fundamental knowledge on microwave engineering, including its applications. So I would like to invite you all to concentrate on the session and take the maximum out of it. And also please note that there will be a Q&A session at the end of the program where you can point out any question and get it answered by a top expert of the field. So with that, let me introduce you the keynote speaker of today's session. This amazing person is a proud graduate from the Department of Electrical and Electronic Engineering, University of Peradeniya. He has earned his MSc and PhD from the University of New South Wales and the University of Queensland, Australia, respectively. He has been the principal researcher of the subsurface radar imaging project funded by SIDA Sweden. And also, he has published many journals and conference papers as well. His main interests are concentrated in ground-penetrating radar design and analysis, signal processing, passive microwave components, and antenna design. And also, most importantly, he is the advisor of IEEE MTT-s Student Branch Chapter, University of Peradeniya from the beginning. So, ladies and gentlemen, please welcome Professor Aruna Gunawardena, Department of Electrical and Electronic Engineering, University of Peradeniya. Dear sir, it's a great pleasure to have you with us today. And without further delay, I would like to cordially invite Professor Aruna Gunawardena to proceed with today's webinar on microwave engineering. Over to you, sir.
Thank you very much for inviting me to this event. I will a very good evening to all of you. I will start the presentation by sharing this. I believe that you all can see my shared screen. Am I correct?
Yes, sir.
Without any difficulty, no? Right, okay. Right. Yes, so this is in this talk is an introduction to microwave engineering. Normally, we do this course in the last year, that is in the final year as a technical elective. So before coming to the seventh semester, most of you are not familiar with the stuff that I introduce here. But even you are whether you are from the first year or from the second year or third year, so I decided to give this presentation to give you a very good starting point in this area, so that you can start working in this area without waiting until you come to the final year. So basically now these are the things that I'm going to address. Basically, I'm going to explain what are microwaves and its applications. And also this microwave engineering demands special techniques, right? And you will see why we need special techniques and what are those. And also I will tell you how to get the start in this area if you like to work, because this is a fascinating area actually. There are many things you can practically do, right? And also I will give you a brief overview of what we have done so far in this area here at the University of Peradeniya. Okay, what are microwaves? In simple terms, electromagnetic signals or waves in the frequencies ranging from 3 gigahertz to 30 gigahertz, we call them microwave. Sometimes this 3 gigahertz, in some literature, they take it as 1 gigahertz. So that is also, there is nothing wrong, right? These are all conventions. Now, the important thing that I want to bring your attention is, now we all know this universal number, the speed of light in free space, 3 into 10 to the power 8 meters per second. And we also know from our A-level days, the velocity of propagation of a wave is equal to the frequency times the wavelength. So if you substitute this 3 gigahertz, right, and 30 gigahertz, right, this 3 gigahertz gives 10 centimeters as the wavelength, and 30 gigahertz, you get 1 centimeter. Just imagine the size, right? It's very small, right? Now the the particular thing that which is important here is now these wavelengths. Now just imagine the size of a printed circuit board that we normally work with, right? How big is it? Sometimes usually something like 10 centimeters by 10 centimeters or 10 centimeters by 16 centimeters in that range. Now, this wavelength is in a comparable dimension. Now, these are comparable dimensions. In other words, circuit or device size is comparable to your lambda. Now, you will see as we proceed, this is not the case usually. For example, now here I will give you some examples. Now, we all know the audio frequencies, we say normally they vary from 20 hertz to 20 kilohertz. So take the highest audio frequency, 20 kilohertz, and using our formula, the velocity equals f times lambda, we can calculate the wavelength. Now just imagine, now earlier we had 10 centimeters to from 1 centimeters to 10 centimeters in the microwave band. Now here, if you take the audio signal, it is 15 kilometers. Now, is this comparable to the size of a PCB? No, not at all. The PCB size is negligibly small when you compare with the wavelength, right? Now again, for example, if you just pick a number like 10 gigahertz as your operating frequency, the wavelength is 3 centimeters. So if you take a quarter wave length, that is 1/4. So we are talking about 7.5 millimeters, very small. So this 7.5 is usually much smaller than the size of the PCB. So your wavelength is actually smaller than the PCB. Whereas if you take a normal signal like audio or power signal, this is not the case. Now you will see that I will give you that as an example later. If you calculate the wavelength for 50 hertz, you get a very large number, right? Now the fact that your whatever the device or the PCB size is comparable to the wavelength makes the things behave very differently. So this is what is happening here. So that is why we have a separate discipline called microwave engineering. Now, actually now we, as I told you at the very beginning, we use very specialized techniques here. Now these techniques we will be using are not only for microwave engineering, but you can also use in some related areas. For example, VHF, and this should be UHF, right? There's a printing mistake. Now VHF and UHF we widely use for TV applications and FM radio. And then beyond 30 gigahertz, we call them millimeter waves. Now I told you at 30 gigahertz, the wavelength is 1 centimeter or 10 millimeters. So now beyond 30 gigahertz, wavelength is smaller than 1 centimeter or in the millimeter range. So that is why we call them millimeter waves. Now here is a very recent technology called the terahertz technology. So from 300 gigahertz to 10 terahertz, we classify it as terahertz frequencies. Okay. So now this gives, what I have done so far is I have explained what are microwaves. So now you have some idea what we mean by a microwave signal. Now we look at some applications. Now you will see that this microwave technology covers a vast area of applications. So which means actually this is something that you must know, right? The microwave technology, because if you don't have this knowledge, that means you don't have in-depth knowledge in any of these applications. In order to acquire an in-depth knowledge, you should have a good understanding of these microwave technologies. So traditionally, microwave engineering was used in radar and also in satellites and point-to-point terrestrial links and in radio astronomy. When I said traditionally, I mean up to about 1980, starting from 1930s, about 1930s to about 1980. So these were the dominant applications. But in more recent times, so here are some emerging technologies. We all know about this mobile telecommunication technology. So the one that is about to come is 5G of fifth generation. And also, I will explain this a little bit. Perhaps you may have heard of radio frequency identification or RFID devices, Internet of Things, right? I will briefly explain this later. And also you find microwave engineering in biomedical applications, and also in these vehicular radars, so that is automotive radar. And also here is another interesting topic, RF energy harvesting. I will explain this, right? Just to give you an overview of applications. So these are the traditional applications. So what you see here is a radar system traditionally used for civil aviation applications. And what you, on the right side, what you see is a radar display, a very traditional one. So here the picture below shows the radar installed on a boat or a ship, right? So these are using this marine radar. So this is a marine radar used in boats and ships. Right now, here is something very uncommon. You perhaps you may not have seen this. This picture that I show you here is not an optical image. So this is a picture taken from an aircraft, but this is a microwave image. In other words, now not ordinary light, microwaves are also electromagnetic waves. So what you do here is, in this what is called a synthetic aperture radar, you transmit a microwave signal, so that is about 3 gigahertz and below 30 gigahertz. Of course, there are synthetic aperture radars operating above 30 gigahertz as well. There are enough millimeter wave synthetic aperture radars. So what you do is you basically transmit a signal to the ground and observe the reflected signal from another antenna. And from that, actually, you create this picture, right? So in other words, so here you illuminate the scene using your own source. In other words, you transmit your microwave signal from an antenna, meaning you can do the imaging even in the night. Whereas to do optical imaging, it has to be in the daylight, right? So you can do nighttime imaging. Not only that, right? You cannot do optical imaging if there are clouds. But these microwaves, they can penetrate clouds and do the imaging. Now, believe me, for example, in our country, although we haven't done, I know that we have the capability to develop a synthetic aperture radar. We are also interested in, we are working in combination with some organizations like the Arthur C. Clarke Institute and the Defense Ministry in these topics. right? We can actually develop. I will also actually, you can also start get involved. I will tell you that later in the presentation, how to get involved in designing synthetic capacitor radars. So these are not just something done in developed countries that we cannot do. No, that's not the case. Point-to-point microwave links we have already seen. So what is shown on the left is actually a traditional antenna mounted on a tower. So basically, if you want to send a telecom signal from one location to the other, like from maybe Kandy to Tegol or somewhere, these kind of dishes are used. What is shown on the right is also a very popular application. So what you see here is some irrigation system. They must be monitoring the water level or something. So what you do is, so it is powered by solar. You can see it's the sensor is located outdoors. You read the signal and you transmit using this antenna to some data logging station located somewhere else. So in other words, this is remote sensing. This is a remote sensing application. And here is another application, satellite communications, right? So the image on the left is actually the now decommissioned 30-meter antenna in Paduk. So until recent times, the overseas telecommunications, all our overseas communication was done using this antenna, but now we have optical fiber under the sea cables. Now, what is shown on the right-hand side is also very interesting. So this is the first satellite Sri Lanka launched into the orbit. This was actually one of the key designers of this is one of our alumni. I believe that he is also joining our question and answer session today. So you will get an opportunity to talk to him, Mr. Peradeniya. So there is a substantial microwave part here as well. Now here is another application. I'm still talking about traditional applications, radio astronomy, right? So basically we use a large number of array of dishes, right, to create an image. Now, if you look carefully in this image, so these are actually, you get the arrays on a Y-shaped track, right? They are just spaced as the letter Y. And now on the right, the top image is an optical image taken with the Hubble Space Telescope, HST. So that is one of the best optical telescopes in the world, right? We have, right? It's in the space, so you don't get any atmospheric effects or anything. So what is shown here in the image bottom, the same object, but done with with the radio astronomy. We're using radio astronomy, right? So this is a microwave image. You can see how detailed this is compared to the optical image. In other words, with the arrays as large as this, you can get much higher resolution than an optical image. So we all now, in other words, they say they are talking about milli-arc seconds. So we all know about arc seconds. So that is 1 in 3000, 1 divided by 3600 is degrees is 1 arc second. So we are talking about milli-arc second. So that is even 1,000th of that. That kind of resolution is only possible with the radio telescope. Now we come to the more recent applications. So as you know, so these are vehicular radars, automotive radar, right? All the new cars, modern cars you see on the roads, even in Sri Lanka here, right? They are equipped with the radar sensor, right? All these Premios, Toyota, Axios, all you get these things, right? Are equipped with what you see. I mean, if you just go to the go out, the cars you see today here, even in Sri Lanka, they are equipped with these sensors, radar sensors. So what you do is, if there is a vehicle too close to you, it automatically applies brake. First, it will alarm you, and then it will brake, right? How does it operate? There is a 80 gig radar operating at 80 gigahertz. So that's a millimeter wave radar, right? Which does that, right? So there are the radar sensors can be, there can be sensors to detect any objects from the two sides or the rear as well. So this is a, now just to tell you, now these things are not, I mean, nothing, I mean, not unreachable technology. For example, in my room here in the university office, I have a evaluation board of a automotive radar operating at 80 gigahertz. Right, it can be connected to a computer, and if you power it, you can detect the objects in the room. So it's automotive radar. So it's that the bundle, right? So these things are available. So present day microwave technology. 5G technology is much wider bandwidth than current these current mobile communication, right? So I'm not going to talk too much about this, but it's a very widespread application, right? It's about now we don't still have 5G in Sri Lanka. Soon we will ultimately have to go to 5G. Even the research is currently going on. Going on 6G technologies as well. RFID technology. The best way to explain is the picture shown on the right-hand side shows two things. This small gadget, which looks like a key tag, is the RF tag. So inside there is a small coil and a resonance circuit and a small chip. So this is the tag here, right? So from an antenna, you transmit a signal to the tag, and you observe the reflected signal. And then there is a tag reader here, right, which is connected to a computer. Now, this RF tagging, now there are many applications. For example, now not in our, for example, I have seen that in literature, you can tag the items in a supermarket using these small RF tags. They are not expensive at all. So just as instead of a barcode, you can use one of these, right? Then all you have to do is, if you are doing shopping in a supermarket or somewhere, put all your goods in a shopping cart, and you just pass through a card reader. That's all. You don't have to even stop. Right, you just take the goods from the shelves and fill your cart and just walk out, right? So this, because you don't need a cashier, or you don't need to pay anything or anything. So what happens is, this antenna transmits the signal, and there can be many items, maybe 30, 40 items in your cart, right? All those items have a unique code, right? It reads those codes, and so you get all the information about how many items you have, etc. And then your bill is automatically prepared, right? And it also reads your credit card number, and you are automatically charged, so you don't have to physically make any payments or anything. All you have to do is get whatever you want from the shelves and walk out from the supermarket, right? So this is one interesting application of RFIDs. Now there are thousands of applications here, right? Radio frequency IDs. So this is also an area we can easily get involved, right? It's not expensive research. Internet of Things. We all know internets of people, but here we are talking about without any human intervention. These various equipment can connect to the internet and do various things automatically. I think the best thing is, if you are, especially if you are from the first year or second year, you may not be familiar with these things. So just do some reading. That doesn't take any time. Now, connected with Internet of Things is another technology called RF energy harvesting, right? Energy harvesting means, now you just imagine a certain sensor used in Internet of Things, right? So you have a certain sensor, say, to measure something in a room, maybe the temperature of some gadget, maybe a boiler or maybe in a whatever, right? So that is automatically read, maybe room temperature, right? So you automatically read it and write it to the, send the data to the internet, right? So that is the job of a IoT. Right now, if this sensor is located in a place where you don't like to visit often, what you do is you can operate this batteryless, whatever your sensor. Now, when I say batteryless, I don't really mean batteryless. There is a rechargeable battery. What we do is we are not going to charge the battery. Now, that is the difference. So in this sensor, it is powered by a battery, but we don't have to charge the battery, right? We don't have to charge the battery. So how does the battery get charged? So that gets charged by picking. Now we know that there are radio waves around us. They are not. We don't use them. For example, there are mobile signals from mobile communication towers, TV signals, FM radio signals. They are all around us, right? So in this RF energy harvesting, what you do is you harvest that energy, right? So basically, there is an antenna to capture this power, rectify it, and then there are power management ICs, and then you can use it for application. So what you basically do is you usually charge a lithium-ion battery or something, right? So in this way, you don't have to charge the device. Interestingly, our department is also involved along with the Arthur C. Clarke Institute and the Ceylon Electricity Board in a project similar to this one. Now that also explains beautifully what is meant by this energy harvesting. What we are doing is we are monitoring medium voltage power lines. So this project is ongoing actually, right? Medium voltage power lines. In Sri Lanka, the medium voltage means 33,000 volts or 33 kV lines. So what we do is we design a small sensor which is fitted to the power line, right? And it is powered this way. It's actually what we, in that particular application, we are not actually harvesting RF power. What we do is we harvest power by capturing the magnetic field due to the power line itself, right? From the we actually capture power from the magnetic field, and then we charge the battery. Then we take monitor the power line, the line currents, etc., and transmit to a ground location located several kilometers away, right? Using what is called the LoRa technology. I will talk more about it, right? There is also a possibility of giving you a workshop on using LoRa. We'll talk more about that during the presentation. Now, here is another very common, very popular application of microwaves. So what is done here is, now this is widely used in these treating heart diseases and also cancers. You can use a focused microwave beam to burn whatever the areas you want. For example, if there is a cancer here, so you can burn that selected area using this RF power. So this is one very good application of microwaves in biomedical engineering. Now, do you know that here is another interesting application. Now doctors use stethoscopes to listen to the heartbeat. But now there is research going on to do this without touching the patient like this, right? So what is shown here is a radar, and this whatever the breathing patterns as well as the heartbeat can be captured remotely using a radar. So this is very useful in a ICU environment, right? So this is actually people believe that in several years time, maybe 10 or 20 years time, stethoscopes will be obsolete. All doctors will end up using these radar devices, which are based on microwaves. So now you can see this scope of microwaves, right? So it covers a huge amount of applications. So you see that actually, in my opinion, if you don't know about this subject, right, you are missing something. So now I have given you a very good overview of the applications of microwaves. Now, at the very beginning, I told you that this microwave engineering demands special techniques, right? Now I am going, now so far our discussion is very simple and not at all technical. I just gave you information. Now I am going to talk a little bit more technically, but its level of technical, the level is even, you can follow even if you are in the first year. So there you don't need any high level mathematics or anything to follow what I'm about to say. Right? Now, when I say that you need special design techniques, whatever the techniques you have to use will be based on wave propagation. You have to take wave propagation phenomena into account if you are dealing with microwave. Simple reason is your wavelength is comparable to the size of the device or the circuit board. So you cannot neglect wave effects. So that is the simple thing. And also, you will be using specialized measuring techniques. Even the equipment are unique to microwave region. For example, network analyzers. Or we have all these equipment in our lab, right? Actually, these are pretty expensive equipment. Maybe one of the most expensive equipment in the lab, right? We have economy models which are not that expensive. When I say it's not that expensive, it's about 7 or 8 million rupees. Right, the expensive ones goes up to about 20 million. That in that range, right? And then some of you may have used various computer-aided design tools to design circuits like Proteus, Eagle, EagleCAD, Spice, Altium, etc. None of those you can use at microwave frequencies. The reason is, of course, the microwave designs needs the wave phenomena to be taken into account. But not these tools, they don't take the wave effects, right? So as a result, you cannot use any of these tools to design microwave circuits. So there are specialized tools, right? And also, if you are using the printed circuit board technology, even the ordinary PCB material that we use cannot be used at microwave frequencies. I will tell you reasons. For example, the ordinary material has a very high loss, right, at these high frequencies. So as a result, there will be an unnecessary power loss. So that is one reason. So there are many reasons why you cannot ordinary material. For example, now I think if you are in the second or third year, perhaps you may have got your, by now you may have got some of the PCBs fabricated from PCB shops in China, right? Now they use the so-called FR4, the very most popular PCB material, and you cannot use FR4 for microwave designs. FR4 is okay for up to about 1 or 2 gigahertz, but beyond that, they are not that's not suitable. Okay. Now I talked about this wave phenomena. Let me explain this in some detail, right? So what do we mean by a wave? right? Let us try to understand this. So I think perhaps this is the only theory part I will be doing in this presentation. It's not very technical, so I have kept the level of technicality and the mathematics to a very minimum, bare minimum, right? So you can easily follow this. So what is a wave? Now, if you take a signal is only a function of time only, something like ft. We all know about sine omega t. If it is a sinusoidal signal, we have sine omega t. Whereas if you take a wave is a function of both space and time. Now, for example, if you have a function f, you can say ct minus z. In this case, actually, you can verify this. The constant c here is the speed of propagation of the wave. I will be explaining in the next slide what I mean by speed of propagation. And also now here is another very popular wave representation. If we have a sinusoidally varying wave, so we have a sine omega t. Omega is basically 2 pi times f, that is the angular frequency, and times b, some constant into z. And this constant we call the phase constant. I will again explain what is this. So in other words, in simple terms, what I wanted to stress in this slide is, if it is a signal, it's a function of time only. If it is a wave, we are talking about both space and time. So let us look at a wave in some detail. Let us look at the speed of propagation. Right? Now here to explain things, I consider a sine wave, right? A sinusoidal wave. Now, what if your wave is not sinusoidal, right? So, of course, it can have any arbitrary shape. Now, for those who are in the first and second year, keep in mind any arbitrary shape you can express as a summation of a large number of, maybe in infinity, maybe finite, a large number of sines and cosines you can express this. So this is called Fourier analysis, and you will be learning this in the second year. And those who are in the third and final year, they are already familiar. So if you are dealing with any a wave of any arbitrary shape, we can always decompose that into a summation of sinusoidal waves through Fourier analysis. So by focusing on these sinusoidal waves, we are not losing any generality, because any other wave we can express as a summation of these sinusoidal waves. Right? Now, if you look carefully, now this what I have shown in yellow, right? So this x-axis is actually the z. So now this is a spatial coordinate z. So now to make the thing simple, I have taken a one-dimensional wave. So it's the only dimension is z. The other one is the wave amplitude. So if you are talking about the electromagnetic wave, so this amplitude can be the magnitude of the magnetic field or the electric field, right? Now the important thing here is the magnetic or the electric field here varies both with time and space. Okay, so now this what is drawn in yellow shows how it varies in space at time t equals t1. So this is just at one time instant. Now just imagine that there is a wave here and you have a camera here and you take a photo of this exactly at time t equals t1. So that photo, I call this a snapshot. So what is shown here in yellow is a snapshot taken at t equals t1. Then after some delta t, you take another photo of the wave, right? So if it is now, then what will happen is you will see that what is shown here in red. So this pattern now is moved to the right by some distance, right? So initially, now this I have marked one point. say if you take this point, right, that point, so it is at z equals z1. So if you take the snapshot at t equals after some delta t time, that point is now moved to this other point. It is moved. So if you watch from this side, what you see is this pattern moves to the right at some velocity. That's what you will observe. Right? Now my question is, what is that velocity? Right? Now, if you look at now these 2 points, now we know that whatever the wave, right? So it can be a wave of electric field or the magnetic field, and it has some magnitude and maybe a phase and also a direction, right? So if this second point after some time delta t, if that also has the same magnitude, right? What does that mean, right? So whatever now if your function is omega t minus bz, as long as this term is constant, you get the same value, right? The function will give the same value as long as this is constant, right? Now I will give you a question to try, right? Now take this down, expression a sine omega t minus beta z, and we know that its velocity is actually defined by this, right? So they say constant points move this way, right? So can you calculate the velocity of propagation here? Quiz 1, find the velocity of propagation of the wave, right? I will give you about 30 seconds because it is that simple. Okay, I think it's enough time. So let's look at the answer. So all you have to do is, if you want the velocity, so we want to find what is dz by dt. Basically, it's omega divided by beta. So this omega divided by beta is called the phase constant. Now let me explain what this a little bit in more detail. Now take any of these snapshots, either the one shown in yellow or one shown in red, right? So now you can see that it is 0 here. If it is sine something, so we can immediately see that the phase angle here at this point that I point here, phase angle is 0. Then it peaks here. Now the total phase angle, that is omega t minus bz, is actually 90 degrees at this point, and now 180 degrees, 270, and now it is 2 pi, right? Now look at this. Now this is the spatial coordinate. This is now whatever the phase of the sine term varies by 2 pi degrees, that is 2 pi radians within that distance, and after that it repeats. So this distance we call the wavelength. So from here to here, it is the wavelength, one wavelength, right? So can you see that in one wavelength, phase changes by 2 pi radians, right? So that is why we call this phase constant is basically 2 pi divided by lambda. So one wavelength, so which is in meters. So this is, what are the units here? Radians per meter. you have radians per meter. Then I will leave it as an exercise for you to verify later. If you combine these two equations, you will again end up with the familiar equation, the velocity of propagation equals f lambda. So if you combine this one and this one, you get this one. Right? Now here is another quiz. Can you do this very quickly? What is the wavelength of at power frequency? If there is a wave propagating at power frequency, what is the wavelength? 30 seconds. Now, these are very simple questions, right? Okay, we know that it is 6,000 kilometers, right? Now, I just wanted you to calculate this to emphasize something. Now, just keep this figure in mind, 6,000 kilometers. Earlier, we were talking about 1 centimeter, 10 centimeter, and figures like that. Now, at power frequencies, at 50 hertz, the wavelength is 6,000 kilometers. Now, just look at this. Now, suppose this is a power line, right? And what is shown in yellow is a snapshot, right? Now, in order to see this snapshot, right? So that is one full cycle of variation. How long the line should be? The line should be 6,000 kilometers. But we don't have 6,000 kilometer long power lines. Now we are talking about a few kilometers from tower to tower, right? So what do you think? Do you expect to see a variation like this if you measure the voltages or currents in a power line? You won't see anything, right? Of course, it varies sinusoidally, but now if you measure the, say at time t equals t1, if the current at this point is 1000 amperes, so I'm talking about the power line, say 400 amperes, just be realistic, right? Typically, it's about a medium voltage power line, about 400 amperes, right? Say at a given instant, if it is 400 amperes here also it will be 400 amperes. Now, since this is now, if you connect the CRO or something, you will see this current or the voltage varies sinusoidally. At one moment, this signal amplitude becomes 0. And at the same instant, the amplitude here also becomes 0. In other words, there is no variation in the amplitude along Z. Right? Now, at another instant, the amplitude peaks. It goes into a peak, and at the same instant, the amplitude here also peaks. In other words, if you take a point, of course, the signal varies sinusoidally with time, but there is no variation in space. Now, this is the case if your length that you consider is negligibly small compared with the wavelength, just as that power example that we took. The wavelength was 6,000 kilometers, and we are talking about few kilometers, so it is negligible. So you don't see any variation along the line, right? So in order to see a variation like this with space, Z, right? Now this has to be at least 6,000 kilometers. But this is not the case when you are talking about microwave circuits. So even if your circuit is maybe 10 centimeters long, if your wavelength is also 10 centimeters, say, right? If it is 10 centimeters, then half wavelength means 5 centimeters. Quarter wavelength means 2.5 centimeters. So just in 2.5 centimeters, 0 can, where if the current is 0 somewhere, just at 2.5 centimeters away, the current can be a peak, right? So now you see the peculiar behavior. Now this is why we need special techniques. So in particular, the technique we apply very often is called transmission line theory. And if we want to be even more accurate, you can use these finite element based electromagnetic solutions, right? And also there are other techniques called the method of moment. So these other software that I told you, they are actually like this, I told you, no, software like Eagle CAD or Proteus, you cannot use for this kind of circuit designs. So these are actually the software that we use, HFSS, AWR, Sonnet, etc., etc. Now, so that is all about waves. Now, this is something that you will be learning in the 6th semester. So even if you are not very familiar now, don't bother about this. You will learn this later, right? Now, if you take what is a transmission line, basically what we mean is, now if you go back to this one, so now there is only one conductor here. Now there has to be, in practice, now there has to be another conductor for the return current, right? So that's a parallel line conductor. And another possible transmission line system is a coaxial cable. So there is a center conductor and there is a outer conductor, right? So whatever the system, so that kind of a conductor system we call a transmission line, right? Now, if the transmission line length is comparable to the wavelength, right? As I told you, along the line, the current will vary. Now, even if you take the time instant, you will observe a variation of voltages and currents along the line. That means you can expect a variation of the impedance along the line. So this equation gives you how it varies, how the impedance varies along the line. Right now, this beta is actually the phase constant 2 pi divided by lambda. Right. So now here I'm just taking an example to emphasize something. Now just imagine your length of the line is quarter of a wavelength, L equals lambda by 4. Right. So then what will happen? Your beta L, now what you have is beta L is 90 degrees, right? So all the cost terms go to 0 and sine beta L becomes 1. So your Z in becomes, now ZL is actually, now you have a transmission line. At a certain point, you look at the input impedance and the transmitted line is terminated with some output impedance. So that is this ZL. So if you do not terminate the line with the impedance, so if you leave it open, so you have an open circuit and then ZL is infinity. So then what will happen? Your Z in is in 0. So what we mean is, if you take a transmission line and if you keep the other end short without connecting, other end open without connecting anything, and if you look at the impedance here, that appears as a short circuit. Did you get the point? It's a very valuable thing. An open circuit will appear as a short circuit if your line length is lambda by 4. On the other hand, you can easily show any short circuit will appear as an open circuit, again, if the line length is lambda by 4. Right? Now, yeah. So again, a very simple calculation for 30 seconds. Now, what do you think? We have already done this, 10 gigahertz. What is your wavelength? 20 seconds. Very straightforward calculation. Okay, you should get 3 centimeters. Now, the reason why I asked you to do this simple calculation is, Now, I told you that a quarter wavelength can transform a open to a short and a short to a open. Now, I have 3 centimeters here. Part of this means about 75, 7.5 millimeters. Agreed? 7.5, 30 millimeters. So, yeah, 7.5 millimeters. Now, look at this. Now, this is a typical printed circuit board that we usually draw, right? Now, I just draw your attention to, now you can see there is a header here. So this is an ordinary PCB, not a microwave one. Now, there is a ground here. Now you can see that one node of this capacitor is grounded this way, right? Now, just how it is, now you can see how it is grounded, right? So with that small PCB track. Now, imagine that if you are working at that 10 gigahertz, if the length of this track is 7.5 millimeters, now you think that you are grounding the signal, but what you are actually doing is you leave it open. Right now, since this is a low frequency circuit, that's okay. But if you do this to a 10 gigahertz circuit, if you try to ground it this way, it will give completely weird results, right? Because expecting a short circuit, you have actually leave it open. So it's not going to work, right? So this is what happens if you try to. Now that is why you need special techniques. When I say special techniques, you will see you cannot just leave this length what you use an arbitrary value. Not only the length, even the line width, the thickness of the PCB, everything needs to be taken into account. Even the dielectric constant, that is the relative permittivity of the dielectric medium, needs to be considered if you are doing a microwave design. Here is another peculiar behavior at microwave frequencies. Now, to explain this, I have just taken a capacitor, but this is equally valid for inductors and resistors. Now, in circuits, we very often use capacitors like this. But keep in mind, now every capacitor, there are 2 terminals like this. No, the connector leads are there, right? Now, those connector leads will have some resistance, R. And when there is a current flow, there will be a magnetic field around the conductor, meaning there will be some inductance. Of course, these 2 values will be very small, right? Very small, but strictly speaking, you don't have perfect things in the real world. In the real world, things are more realistic. So in addition to the capacitance, you have some resistance and inductance as well, although you don't like it. Now here is another question for you to try out. Now, especially those who are in the second year onwards can easily answer this. What is the impedance of this circuit at the angular frequency omega? Again, 30 seconds. Can you very quickly write it down? Okay. I will give you the answer. This is the answer. Right? You know that R is there. This has an impedance of j omega L, and this has 1 over j omega C. What do you think? What happens if omega is this value, this particular value? Just to try out, just to multiply both the numerator and the denominator by j of this last term. and then you will see what will happen. What will happen if this is the case? The impedance of this is a positive j omega value. The impedance of this one is a negative impedance value. It's minus j something, right? So these two will cancel out and you will be only left with R. Exactly at this frequency. This frequency we call the resonant frequency. Now, what's happening here? Now you have a capacitor, and when you try to, as you go higher and higher in frequency, there will be a point this capacitor is going to behave as a pure resistor. It's no longer a capacitor, it will be a resistor. Now, this particular point we call the resonant point, and this particular frequency we call the resonant frequency. In other words, the capacitor resonates at that particular frequency. What will happen if you try to operate beyond this frequency? If your omega is larger than this, then this term will be more positive than this one. As a result, you will end up with some positive j omega something, meaning your capacitor now acts as an inductor. See, now you start with the capacitor, but if you operate beyond the resonant point, so it's going to be an inductor. It's not a capacitor. It's not going to behave as a capacitor. Now, believe me, actually, now we have two microwave courses. One, an undergraduate course in the 7th semester, and there is a postgraduate course. Especially in the undergraduate course, we have a lab on this topic. Now, when you do the lab, you will see, if you take a normal ceramic capacitor, which are supposed to have the highest resonant frequencies, if you consider ordinary capacitors, right? They will resonate around few megahertz, after few megahertz. Forget about gigahertz. So what will happen if you use these easily available capacitors in your microwave design? Your circuit is going to definitely fail, because your capacitors are not going to work as capacitors. Now, same theory applies to the inductors. Your inductors are going to behave as capacitors, and vice versa. So you have to have some control over these things, right? So now this is why we need special techniques. So now I'm actually introducing microwave engineering to you, right? So you can see that your normal design techniques are not going to work here. Now I showed you the applications, the vast variety of applications available for microwave. But in order to practice it, to be competent with those things, actually this is what you need to know. Now I will show you something. Now this is actually something done in the third year. So these are called waveguides, right? So they are just like tools. Cross section is here, a rectangular cross section. Yes. Now there is a rectangular. Now this has a rectangular cross section, but it doesn't have to be rectangular. It can have any other shape like circular cross sections, etc. All right. So there are many devices like this. So these are so-called tube devices. You will be learning again in the 6th semester. So these are for microwave, high power microwave, right? Now again, I will ask you a very interesting question. This is a quiz, right? Very important question. Important question. Now these are two current carrying conductors, right? So capital I flows this way and the return current comes this way. I will ask you a question. Now this carries energy from one location to the other. where is this energy actually? Where is the energy carried? Through the conductors or by some other means? What do you think? Do you think that the energy is carried by the conductors? Can somebody answer? Yes or no? That is very helpful. It doesn't matter. Don't be shy to give the wrong answer.
So isn't it through the space because there's a magnetic field created by...
Exactly. That is the answer, right? Don't think that it is the energy is carried by the conductors. Actually, the current, it is true that the current is carried by the conductors, but the energy is carried by the field around it, right? Not the conductors. Now, to this is much easier if you look at this one. These two equations you may have come across in the first year. The energy density, right? It's basically the energy density is half of the D dot E, and the magnetic energy density is B dot half of B dot H. So that means wherever you have an electric field, you get electric energy, and wherever you have a magnetic field, you have magnetic energy, right? So in this case, now if you imagine a perfect conductor, so what is the electric field inside a perfect conductor? That is zero, right? There is no E is zero, so there is no energy there, right? Energy is actually, there is electric field around these conductors. So actually, the energy is in the field, right? So now what is happening is, now if we are talking about a wave, now this E and H actually vary with time and space, right? So it varies with time and space, and the wave is actually guided by these two conductors. So that is what is happening. Now this is guided by the two conductors. So for example, if we bend the two conductors by 90 degrees, the wave will also bend by 90 degrees. Okay. Now we all know that, I mean, if you have a current source here, and if you bend the two wires, the energy is not going to escape this way, no. It will come to where the wires are, right? So it will follow the wires, right? So in other words, energy is guided by the wire, and it's actually guided by the wire, by the two wires, and it is in the space in between. So if that is the case, what is wrong in imagining that you can send energy through pipes, electromagnetic energy? Now that is exactly what we do in the case of a waveguide. So because why I particularly mentioned this, particularly if you are from the first year or second year, you might wonder that there is only one conductor. So how do you send some energy from one point to the other one? So it's, you might tend to think that you need two conductors to send energy. No, right? Now in this case, the wave is actually guided by this conductive wall, the cylindrical wall, right? So energy actually, just as you you can pump water through a pipe, you can pump electromagnetic energy through a conductive wall like this, which we call a waveguide, right? So that's an introduction to the waveguide for those who are not familiar with this from first and second years. So we have a waveguide kit in our lab. So I'm just, so this is actually will be using the third year experiments. So what is shown here is what is called a klystron. People think that this is outdated. No, it's not. It's not. These klystrons are still used at very high microwave frequencies, and also at very high power to generate very high power microwave. Now, still I'm discussing why we need special techniques for microwaves. Now, if you are using, now one technology is the waveguide technology, basically using pipes to send electromagnetic energy. And then you have PC, printed circuit board based technologies. And these MMICs stand for monolithic microwave integrated circuits. So these are the IC integrated circuit or IC equivalent at microwaves. And this LTCC is a technology which is called low temperature co-fired ceramic technology. We are not going into the details. So this microwave technology you can implement in a large number in a large number of ways. So there are many other ways as well. So I will very quickly go through this one. So we are more interested in the printed circuit board based technologies because we can actually practice that technology in our lab, right? So basically now what we do is, now this is very similar to an ordinary PCB, but the only difference is one side is a copper plane, entire copper plane, and you have the circuit here. So all these widths, heights and everything you have to control. So this is called a microstrip line. So here we have two ground planes and whatever the conductors are in the middle. So we call this a strip line. And then we have two ground planes on the two sides and the conductor in the middle. There is no ground plane, so it's called a coplanar waveguide. Here we have a coplanar waveguide with grounds, plot lines, and various other technologies. Okay, here, as I think I have already mentioned that now one thing is circuit dimensions have to be very accurate. Right, so in other words, line lengths, widths, they have to be very accurate. Otherwise, your operating parameters will vary. So you have to carefully control all these parameters: PCB thickness, relative permittivity, loss, cover heights, everything. So these are some of the. Now here is an example of microstrip circuits. So what is shown here are some microstrip circuits that we have fabricated in our lab, right? So for undergraduate labs in the third year, in the final year, right? Now here to show you how this is used in practice, what is shown here is a spectrum analyzer. We have spectrum analyzers in our lab. If you open up this particular, now I have taken a particular example. Inside it looks like this. Now these are the microwave circuits, right? So these are all microwave circuits. So you can see how microwave technology applies inside this modern equipment, right? What you see are very sophisticated modern equipment, but inside it is the microwave principles that you apply here. And so microstrip versus waveguide. So now what is shown here is a microstrip low band pass filter. The same filter you can implement as in the waveguide form this way. So these are called cavity filters, right? So from the outside with the cover, it looks like this, right? The waveguide filters, they have very high performance compared to these, right? Performance is high and they are more expensive. And then showing you MMIC technology, microwave integrated circuit technology. This is the IC equivalent. So the size of a microwave IC is something like this, right? Very, very tiny. So what I have shown is a microwave monolith MMIC of a amplifier circuit available in the lab. So what you have on this side is a 5 rupee coin, right? So this chip shown on the right is a entire radar, 24 gigahertz radar in a single chip. So this is called a system on chip, SOICs, right? So you can see it's all microwave working at 24 gigahertz, right? This one, I got this from Mr. Aruna Gunawardena from the Artistic Lamp Institute. This is a satellite communication module he has developed based on the LoRa technology. So you can see again the MMICs, how they are used, right? So these are local applications. Then I told you that we use specialized software. So this is HFSS, right? So you can see that it's different from the traditional software like EagleCAD we use. Okay, now I have finished explaining why microwave, why you need special techniques. Now we come to a very important thing, how you can get the start in this area. Firstly, in this society, we plan to give you a workshop, several series of workshops. We have already planned to give you a workshop conducted by Mr. Aruna Gunawardena on designing an antenna. Now, if you look at the, now I told you a large number, showed you a large number of microwave applications. Now, if you look at all those applications, there is one thing common to all of them. There is a transmitter inside, there is a receiver inside, and there is an antenna. There are antennas, one or two antennas, right? So we make transmitters, receivers, and antennas at the microwave region, right? Now, this, so it's all now, for example, if you take a satellite communication system or mobile communication, maybe your mobile phone, inside the mobile phone, what you have is a transmitter and a receiver and antennas, right? So it's all about designing these three things, right? So in our first workshop, we will start from the antenna design part, right? So you will learn how to design an antenna. Mr. Aruna Gunawardena will explain what he has in mind. And if time permits, I also like to give you a workshop emphasizing the principles behind receiver and transmitter design. Right? So as we don't need any licenses for receivers, I will show you how to design an analog receiver. In fact, the receiver is more complex than a transmitter. So if you can design a receiver, designing a transmitter is very simple. Right? So now this will expose you to designing a receiver. Right? Now, believe me, now in these workshops, we are aware that some of you have not done these things. You may be in the second or first year. So we will teach it in a way that even if you are in the first or second year, you will be able to do the things, right? It's important that you get some hands-on touch by doing these things. Then it will be easy for you to follow the courses later in the course. And then again, if time permits, Mr. Aruna Gunawardena will teach you this one. How to design a remote data link using LoRa. That is, so this is something very useful for the industry. Actually, there are thousands of applications you can think of. For example, take irrigation department. So they have reservoirs and they need to monitor data, right, remotely. Take the electricity board, right? You name it, right? This remote data logging is a very popular application, and actually you can get a real hands-on touch by actually now most of the time what is happening in Sri Lanka is we are not going into manufacturing these things, we just import. Right now, you know that we have problems with dollars, so it is time to design our own things, right? So there will be a very big demand. Now, when you do these things, of course, you may have to do your own reading and learn things. I recommend this particular site. So it covers a very large number of topics. It's almost like actually it's an encyclopedia with various videos, tutorials, so many things. If there's anything unknown, you can search and find enough teaching material in this microwave101.com website, right? There are many other sites, but I'm not going to put all those things, then you will be confused. So I just recommend one thing, you start here, right? So even if you are in the second year, it doesn't matter, first year, right? You can still get something out of this if you have time. Now, by the way, now this is actually now this learning, so not only for microwave engineering, it applies to various other things as well, right? Now, we are learning this not just to pass an exam or subject or anything. So you should have a passion for doing these things, right? You should enjoy what you are doing, right? Now, to get the maximum out of this microwave engineering, just having just knowing microwave engineering alone is not enough, right? Actually, what is more enjoyable, or what you can really enjoy is if you can make something, right? So that gives a lot of satisfaction. In order to do that, in addition to microwave engineering, you should know your digital and analog electronics you learn in this course. And also you should have a very good knowledge of practical knowledge of embedded systems, right? Right. And then also you should know programming, right? At least one language, right? And so it will be very useful. So do these as, so I think I also recommend you to have a small workshop, a small space at home to do your things. Of course, I know the money is difficult these days, but you can start very simple. To start, maybe you can just buy a soldering iron, less than 1,000 rupees, as I know, right? And some solder, and you can start doing your soldering at home, at least to save some time. So this is not going to end just after final year or anything. So you can build your workshop as you mature as an engineer. Okay. And also now I will show you some few more other things. Now, these are some of the things that we have done in our lab, right? So what we have done so far. This actual antenna we built several years ago, but now I think it is dismantled. Unfortunately, now this is the version 1. So we were trying to build a, this was supposed to be the antenna of a radio telescope, right? But this was version 1. Unfortunately, we couldn't go for another version because one thing is the design of this one. Mrs. Sena retired, and also there were the universities was closed due to COVID and various things. So why I showed you this picture is, although we will not be proceeding with this antenna, now I told you the things that you can do are here, right? We will be giving you workshops, and then you will learn how to do design transmitters, receivers, LoRa-based things, and like that you can get some hands-on exposure. In addition to this, now this radio telescope project is also something ongoing, right? Now this is what we have done in the our faculty. Now you see that now the picture shown here, this one is a radio image taken by this very small antenna. Even with the small antenna, I think this is about maybe 1.5 meters, right? With 1.5 meters, you can still get a good image. So we have got some 3-meter antennas with us. I think it's 3 meters, 3 or 2, I'm not sure, maybe 2.5, right? So you can actually start this radio telescope project is also open. So you should be able to get better images than this if somebody is interested. We couldn't do these projects in the past 2 years due to the closure due to COVID. And also, this is also another project that we were interested in. I told you that synthetic capture radars are within our reach. So if you want more details, you can type coffee can radar in Google and search for this. So this is actually a course developed by MIT Lincoln Labs, right? So where they teach you to design a synthetic capture radar. So here we have to buy few components, and so you can see that the two antennas are actually made of coffee cans. So this operates at 2.4 gigahertz. And the picture taken with this is here. You can see that the pictures with very good resolution they have taken, right? Actually, we have also been involved in doing similar projects. For example, this is finally undergraduate project we did last year. and that group very successfully did this project, right? They almost finished it. Unfortunately, we couldn't solder the things and test because of COVID, right? So we designed a Doppler radar to measure the speeds of speeding vehicles in a highway, and then transmit that data to a ground station using the LoRa technology, right? So there they use this AWR microwave office, that specialized software, the schematic diagram, and this is the test layout board that they have got, right? So the only thing is we could have easily fabricated this and tested, but couldn't do it as the university as we worked online. And all this radar performance was also simulated using this tool, right? AWR. So you can see what you can do with this. And also now we are coming to the end of the presentation. So our micro lab is also very well equipped, but this dark room and these things are now dismantled due to the ongoing construction. But still, we have set up these things in our new building, so we can still use them. And so these are the facilities available for you. And we have very good and very expensive measuring equipment, right? This we have been using since year 2001. Pretty expensive network analyzer, and this goes up to 13.5 gigahertz. This one is both a spectrum analyzer and a network analyzer, which you can use for measurements up to 26.5 gigahertz and so on. These are also spectrum analyzers. Some noise figure measurements we can do. Some of the test fixtures we have made in our lab and so on. These things all locally manufactured. Interestingly, now I actually bring your attention to this piece. So this is a test fixture. This costs about, I think now it would cost about 2 million rupees. But we built it in our lab for about maybe 15,000 rupees several years back, made in Sri Lanka. So these are also all made in Sri Lanka, these things, right? And these were built by our expert mechanic, Mr. Kumar, you may have seen in our lab, right? And lastly, before I finish, I want to show you that when you say microwaves, many people think it is the engineering about this gadget, but this is only a minor application. In fact, I have never worked with this other than cooking, right? And I think with that, actually, I end my presentation. So I have almost taken 1.5 hours to finish. Any questions we can now take?
Thank you very much, sir, for that very informative session. I hope our participants could learn a lot of new things regarding microwave engineering from your presentation today. And also we have noticed that Dr. Walluwa, the chairperson of IEEE MTT-s Sri Lanka section, is also joined with us today. So we highly appreciate your presence, sir. So now it's time for the Q&A session where our participants can directly raise their question to our speaker of the day. So I would like to encourage you all to grab this rare opportunity to interact with this expert of the field and clear out any of the question you have. You can simply unmute yourself and raise the question. If not, please direct it to the Zoom chat box so that I can raise the question for you. So our participants have already sent us some questions. So the first question is, using the RF energy harvesting method, is it possible to generate high voltage, or does that valid only to generate a small power?
Yeah, it is for small power actually, right? Don't think that we can generate megawatts, no, right? As I told you, to power things like IoT sensors, right? You can use because the what we harvest is also a very small amount, no, right? The incident power is a very small amount, right? So you can so it is for very low power applications.
Okay, thank you, sir. So the next question is, what are the main usages of MW images taken from synthetic aperture radar, and how far MW images can be used compared to optical images?
Yeah, they are used, for example, widely used in remote sensing applications to monitor deforestation, uh, so in agriculture, and also in the defense industry, that is for mainly for surveillance, right? So there are so many applications of synthetic aperture radar.
Thank you, sir. So the next one is, what are the special CAD tools that can be used for microwave designs as students?
Yeah, we currently use AWR Microwave Office. So it is actually by Cadence. It is freely available for undergraduate teaching. So we already use it for courses. If anybody is interested, please contact me. I can set up permission to use our license.
Thank you, sir. Next question is, though RFIDs can scan multiple objects in a range, how collision can affect the process? Means, can readers and text be collided? If so, what are the technically feasible ways to mitigate those malfunctions?
If there are collisions, actually, I believe there are protocols. I'm not really into that much details. If there is a collision, of course, as in this Ethernet, so there are collision detection algorithms. No? So they of course, now there is no unique method. So from application to application, things may vary, right? But now each of these RFIDs, they have a unique address, right? So they are now, for example, if you have 10 bits, you can have 2 to the power 10 combinations, right? 1024, right? Combinations. So likewise, not 10 bits, you can have a large number of bits. So that way it is unique. There are techniques to avoid any these collisions. So they can be time division, they can be frequency division. So that's another field actually. It is there.
Okay, sir. So the next one is, what are the limitations to make a aperture radar in a country like Sri Lanka?
You can do that at a very small scale, right? As I told you, that this coffee can radar, we can even build in our lab, right? So now if you look at, if you search internet, you will see that there are 2 versions they are talking about coffee can, right? One is the using these so-called connectorized components, which is the very first and the original one. When you say connectorized, so for example, if you want to use an amplifier, you use that amplifier as a block, right? So it comes with 2 connectors. That is a bit expensive. And the cheap option is to use integrated ICs and make your own PCB, right? So I think, as I remember, that connectorized version of this coffee can was about $350, whereas the PCB version was only $50, right? So that is that one. Now, actually, this year I have given, now the coffee can is 2.4. This very same radar I have given as undergraduate project this year. It's current. To do the same at 5.8 gigahertz. So you have to design the whole thing, but at 5.8 gigahertz. So, and our plan is actually, if we come up with the boards, now we have recently got there is a UAV available, a quadcopter available in the lab. So we have, if we succeed, we will be installing it in the quadcopter, and we will be able to do some imaging in the faculty. So it's perfectly feasible. And then of course you have to operate it outside, you have to get licenses and all that. So what I said is, now these things can be done in Sri Lanka.
Okay, so the last question is, are there any harmful effects of overexposure to microwaves of these applications?
Yes, there are limits imposed. There are safety limits, right? If you exceed those, it is harmful. That's true, right? So now as an engineer, when you design the things, you should make sure that you operate below those limits. Not only that, even at the design stage, so once you have done the design, you have to verify that through measurements. So now all your things that you use, like mobile phones, they have to get certification. You have to actually, so we say that you have to comply to those, there are international standards to ensure safety, right? You have to comply to those standards, and you have to verify that through measurements. So once you have done it the correct way, so it is safe.
Thank you so much, sir. So since we don't have many more questions, we are going to conclude today's session. So dear sir, thank you so much for taking.
Hi, I have one question. Is it too late to ask?
No, it's okay.
Hello, Dr. Arun. I don't know whether you can remember me after a long time. Back in 2020, before Corona hit, there was a satellite workshop at University of Peradeniya.
Yes.
Yes, I was undergraduate from SLIIT back in the day.
Yeah.
So yeah, I have two questions. So one question is that you said about terahertz frequency range. So
yes.
Is it like when we reach the terahertz frequency, does it have any correlations with the optical region as well?
Little bit below the optical region.
Right.
We are not into the optical region. Yeah, we are below that. Below the optical region.
Below the optical.
Just
okay.
Below.
My second question is like now for optical communication, most of the time, I mean, almost all the time, you need line of sight.
Yeah.
I mean, because we use fiber optical cables because we in order to make some artificial line of sight.
Yeah.
What property of the wave which does it enables microwaves to not have my line of sight? I mean, microwave does not really need to have line of sight to operate. What property of wave is that? Is it because the wave particle duality of photons?
No. It's like this actually. To some extent, actually, it's good if you have line of sight even at microwave. Yes, I know that you can have non-line of sight links. They actually rely on diffraction. The property is diffraction, right? The waves diffract. So when we say say if you have a hill or something, right? So actually, now the normal theory is ray optics. So everything travels along a straight line, no? Right? When it hits a sharp edge or an obstacle, the wave gets diffracted and it bends, right? So it is diffraction which causes non-line of sight possible, but of course the signal strength drops severely, but still it is possible. Yeah, it is diffraction.
Right. Thank you, Dr. Arun.
Also, I'd like to thank our MTT chair, Dr. Raghupati Raj Valuvan from Jaffna University for joining this. We are very glad to see you here.
If there are any more questions, you can ask now.
Yeah, it's my pleasure. Thank you for conducting this workshop. I believe we can get more students and practicing engineers interested in this area. Thank you very much again. And I'm glad to see that some more workshops are being planned. We hope to get more participants and as much as possible.
Exactly. Actually, I talked to Dr. Valuan, and also we discussed the possibility of putting you in touch with the students of Jaffna University, because they will also be very much happy to work jointly with you in this area.
Yes, yes, definitely. Yeah, I'll get somebody from our Electrical and Electronic Engineering Society to get in touch with you. So we can also establish another student branch chapter there.
Yes.
With your help, yes.
We can certainly help. Now, this is an area which is not very developed in the country. So that is why we encourage people to actually get involved, even the other universities. We should actually initiate this.
Definitely. Thank you again.
I'm not sure whether Mr. Tharudu Dayaratna is here. Can anybody check? He's told me that he will try to join, but I don't know whether he's here. Probably
It's not here, sir.
He's not here. No? Yeah. He's the other resource person, actually. He's going to doing the micro lectures with me in the final year. Okay, then
So thank you so much, sir, for.
Yeah, I think shall we wind up?
Yes, sir. So thank you so much, sir, for taking time to raise the technical capabilities of us on microengineering despite your busy schedule. And we all were able to have a better awareness from the presentation today. So please accept the token of appreciation from IEEE MTT-s Student Branch Chapter, University of Peradeniya. And furthermore, I should not forget all the participants who attended this evening. So without you, this event would not have been a success. And also, I have a request from you. Please do follow IEEE MTT-s Student Branch Chapter, University of Peradeniya official Facebook page, so that you can get to know our upcoming events without missing any of them. This remarks the conclusion of today's webinar. Hoping to meet you all in the upcoming events as well. Until then, stay safe and have a good night. Thank you.